Okay, let's begin. So we're going to be looking today at logic layouts. So what we did last time is we looked at some general design strategies, and then we looked at process flow, we looked at N-wells and P-wells and so on, but mainly we were looking at single transistors for that. So what we're going to move on today is something a bit more complicated than that. So we're going to start looking at how you put together gates. So we'll start off with fairly simple gates and work out how we actually arrange the silicon and physically lay these things out. So the example we've got here is a NOR gate with two inputs, A and B. And remember, this has the two NMOS transistors in parallel and the two PMOS transistors in series. And we can, for instance, choose that the width would be the P type would be twice the width of the N type. We, of course, need also a power supply. So you've got VDD and VSS down here. And we've got an output Z and two inputs A and B. So that's the circuit diagram. What we need to think about is how we turn this into an actual physical layout on the silicon. So let's begin by counting how many transistors we need. And that's relatively easy. We need 4 transistors. And so what we're going to do is we're going to put some embryonic transistors there. We know they need an active layer, that's the green. And what that basically is, if you remember, is where we etch through the field oxide, so we have access to the underlying silicon. We need to put down the poly, which is used for the gates, that's in red. And we also will need source and drain contacts. At this point, I'm not worrying about the different size of everything. We just want basically how it's going to be there. So that's that, and we know that we need different implants for the PMOS and the NMOS and so on, but we're just starting with something fairly simple. And what we want to do next is we need to identify where we can merge things together to save space. And that will help us to reduce the size of everything. And that also helps us to reduce the capacitance and the resistance, and so it makes things faster. So if you've got transistors in series, you don't need the intermediate source and drain contacts. So you can merge them like that. So basically, you've got 2 transistors here in series. Just draw it quickly like that. These are PMOS, but it doesn't actually matter particularly whether it's PMOS or NMOS. The same happens to each of them. When you've got them in series, you've got your input here. So goes through one transistor and immediately into the next transistor. So these 2 contacts here are joined together. And actually going up into a metal layer and back down onto the silicon just adds resistance, it adds space, it doesn't help in any way. So what we can simply do is merge it like this. And in this context, this would be, for instance, the A contact, and this would be the B contact. And of course, both gates A and B would have to be active before current will flow from one end to the other. So that saves space. Now, that's with series transistors. Parallel is a little bit trickier, but we can still make some savings. So if we look at the NMOS, we've got two transistors in parallel here. So basically, parallel means something like this. Excuse my horrible sketching on this system. Something like that. So, okay, this is our ground at VSS, and this will be the output. So if we look at these here, we could say, well, that's ground, which is our VSS, and this is our output Z. And again, the next one, you could say that's ground, and that's the output Z, but it's a symmetrical system. So what you do is you flip this one, and you put the ground there, and the output there. And if you draw it like that, then you can immediately see that these two can be joined together. So these are our grounds, or VSS, or however you want to call it at this point. A bit slow typing it. This is our common connection here. And by doing that, you're saving space, because again, you don't need to have an interconnect connection between these two like that. That's not necessary at all. So the parallel transistors are not as compact as the series one, but you can still reduce the size. Right, the next thing we want to think about is T-sizing. And if we look again at our circuit diagram, we can see that the stack depth on the P side is 2, and the stack depth on the N side is 1. So we've decided we were going to use a size ratio of 2. So that tells us that these widths are going to be 4 times our unit width. So what does that tell us? Well, that's where we had before. We're now going to size them. And the PMOS then needs to be 4 times as wide. Now, the important width is the width of the open area of silicon where it's going to get implanted. And it's the green hole in the field oxide that matters. It's not the length of the polysilicon, because the length of the polysilicon is, as you can see, it extends beyond the opening in the field oxide, and that's because of what we were talking about last time, that we need to do the alignment, and it does need to extend. But these bits of gate which extend beyond the opening, these are on top of the field oxide, they have no direct influence on the device. The actual device is all in the green area. So that's the bit that gets multiplied in size by 4. We want better contacts to it. So if we put extra via holes, extra contacts there, it gives you a lower resistance contact at each end, and that's a good thing. It doesn't cost anything to put these extra ones there, because it's all going through the processing together in parallel. We open all the vias at the same time, we metallize at the same time, we etch the metal at the same time. So this doesn't cost us any extra, but what it does do is it reduces the resistance. And if you reduce the parasitic resistance to the transistor, you make everything faster. So that's what we're saying, that the width is defined by the active, not by the poly. So the next thing we need to think about are the local interconnects. So the gates, the poly, need to be connected to something, and we need to metal layer as well to join up the various outputs and inputs. So if we do that, we get to here. And what have we got? Well, we've got two inputs. So these gates are inputs, which will be A and B for the NOR gate. So we call that one A if we like, and that one B for the moment. And then we need an output. So that will be the output. And remember that I said the outer of these two we can connect to VSS. So these ones go to ground here and here. And this will be VDD. So a bit slow drawing this, but that's going to be our ground. Sorry, that's our power rail. And this is our 0 volt. Likewise here, my lights are not working. Okay, so there we are. So that's the basic connections. What we need to do next is think about another issue, which is the body effect. And we've really just ignored this up to now. But if we want a MOSFET to work, we need to correctly connect up the body, so because it's the difference in voltage between the gate and the substrate which will give rise to the conducting channel. And this then gives rise to a threshold voltage, and we want the threshold voltage to be well defined. And if the substrate potential changes, then the threshold voltage will start to change, and we then end up with all sorts of problems with our circuit. So if the threshold voltage changes because the substrate's changed, then the currents change. The threshold here is for an inverter, so it's we're starting to look at the circuit situation, and it has a threshold as well, and it depends on the thresholds for the P and the N transistors. So if the substrate voltage shifts, it means the whole circuit starts to behave badly. We can think about this in terms of the energy diagrams, which we were looking at way back at the beginning of the course. We're going to look at them quickly, but if you remember, we've got this represents the gate here. This is the semiconductor channel with the oxide in the middle. And as we put a positive potential on the gate, on this diagram, it pushes this down relative to the potential on the substrate. And eventually you end up with an inversion region here, which becomes N-type, and your NMOS will start to conduct. You'll have the transistor being active. Now, this is the case with the substrate at 0 volts. If the substrate potential drifts upwards, then you don't get the channel forming, or you don't get it forming at the same potential. You would need to increase the potential on the gate and push this down further. And that causes the problem. So positive voltage on the substrate means that you need actually more positive voltage on the gate to reach the threshold, and the whole performance of your circuit will degrade. So let's move on. Sorry. Sorry, just looking at the chat there. Yeah, is a transistor in a pinch-off state then? If the substrate of the body potential for the NMOS rises, then it is pinched off. Obviously it depends on the relative potential between the gate and the underlying semiconductor. So if the semiconductor potential goes up, then we need a correspondingly higher potential on the gate to actually enable conduction. And yes, you can just pinch it off by rising the substrate potential. So, okay, you can do some maths around this. This is not what we're going to study in detail here because this is not a transistor course in detail, but you can write down the equation for the threshold in terms of the threshold at 0 volts, Tn0, and various parameters. So you've got so this is what it would be if the substrate was at 0. Here we've got now a substrate that's floating, and you can obviously see that as this value V rises, then the threshold voltage will rise. So the problem we have is that any voltage drop through the semiconductor substrate will change the body voltage across the chip. So if you think about the way we've looked at the NMOS transistors up to now, we've said, well, you can start with a wafer, which was p-doped, and you locally have your N-select implants and so on. And you can imagine that you could, in that situation, connect the whole chip, the body of the whole chip, to ground somewhere near the edge of the chip. So you've got all your contacts around the edge of the chip. You could have one or more ground connections holding the edge of the silicon to 0 volts, but because the semiconductor is resistive, you can have a change of potential across the substrate, and it can cause problems. So what we need to do is to use substrate straps or ties. So what we do is we locally fix the substrate potential to what we want it to be. So it needs to be VSS or 0 for the NMOS, and it needs to be VDD for the PMOS. And rather than relying on a single connection right at the outside of the chip, what is needed is a local connection at every single set of devices. So how does that work? Well, if you're looking at a single transistor, what we've got is your source, drain, and your gate here. And we then have a strap locally connecting it to ground. So what we do is we implant a local area here, strongly P. So we know that the whole wafer, we're thinking, is basically P-type, but to make a good connection to P-type material, because it's a low doped P, to make a good connection, you always need a heavily doped area. Just like these connections here, you have a heavily doped end select region, to make a good connection to the local body area, you need a heavily doped P implant just here. And then you need to open it up, open the field oxide up so you've got access to that area, and you put down your vias, little black squares, and the metal, so you connect it to ground. And in the same way, we need to do the same thing on the PMOS side. So we've got an N implant here, heavily doped again, so that we are tying this area now to VDD. So you've got this large N well in which the PMOS sits. This area here is a heavier doped N implant, which is what you need to make good contact. And the straps, as you can see, are connected as closely as possible to make these body connections. So again, we've shown the body connections here and here. So if we go back to our NOR gate, what we need to do is put in these straps. So we also need to do various other implants as well, because our PMOS needs some P-select, some P-doping here. The NMOS needs some N-doping around here. So if we do all that, we can see we've got the N-select here for, sorry, this is the P. This is the P-select around here for the PMOS. We've got the body connection up here, so we extended this connections here to the transistors and made a connection to the local body area. So strap here for VDD, strap here for VSS to for the NMOS. And then finally, what we needed was the N well for the PMOS transistors. So once we've got all that, we can start to label it. We've got our input A, our input B, our output Z. We've got VSS and VDD. And that's the complete layout for the NOR2. Now, all that is something which we can do using a computer. Computers are great at designing things, and then they can be transferred to a mask and fabricated. But sometimes it's quite nice just to be able to quickly doodle how we want to arrange our gates and think about different ways to organize the layout on the silicon. So we can lay this out, we can carefully draw all these rectangles and lines and connect them all up. But what if we want to actually think about 2 or 3 different ways we might do that, different organizations? Is there a quicker way we can just doodle and arrange our gates? So this is where we come to stick diagrams. And the idea of the stick diagram is that we are basically doing a quick sketch. It's simplified, so we don't put in all the detail. For instance, it's not going to be completely to scale, but we're more interested in looking at the topography and different arrangements. So I'll go through how we do that with a number of examples. Somebody's just asking about the previous one. Can you switch VSS and Z without issues? You can certainly swap them. So you're saying, could this one here be VSS and these ones here in principle could be Z? I think the answer is yes. You would have to rearrange the way you've drawn this. So yeah, imagine instead of the blue line here being like a U shape, it would be like an upside down T. You would need to rearrange how this came. So yes, in principle, you can do that. In practice, you're going to look to see which one gives you the minimum resistances overall. Don't know if that helps. Right, so let's look at the stick diagrams. We're going to look at an inverter, and what we're going to do is we're going to draw two very, if you like, prototype transistors, and do them in a way that's relatively straightforward to draw by hand. So our polysilicon is just a line. Our vias and metal contacts are just a cross. And I've just drawn a rectangle for the opening in the field oxide. Now, this is using different colors. I've got red, black, and green. You can do this in monochrome. You can try and be, what's the word I'm looking for? It's a little bit trickier in monochrome to some extent because we haven't finished the device yet. And you can imagine that at some point we're going to need to have the metal one layer, and it's much easier to draw the metal one layer as a series of lines which are different color to the red ones, but you could, of course, make them dashed lines or something and distinguish them that way. So you can do this in monochrome. Doing it in color is generally easier to do and easier to see. So we've got two transistors. One's going to be the P, one's going to be the N. And okay, I've got my poly and my metal joined up now. So if you think about the way an inverter is, just draw the inverter up here for a second. We've got the output here, and we've got these, oops, I need to make sure that's a P, and these two are connected to each other. So that's the input. So you can see that here, we've got the inputs are the gates connected to each other. The output, again, I've done the same message in the NOR gate. I've made sure the outputs are close to each other. Just make life easy. And then here, of course, we will have VSS and VDD. So we can draw those in, and we need some implants. So we can draw the implants. So we've got the N select here, we've got the P select here, and we've got the N well here. Starting to look a little bit more complicated, but you can still see that you can draw that fairly quickly by hand and just see what it looks like. Then we can start thinking about how we're going to arrange this. So I've drawn it like this initially, but that's not the only way we can draw it. Okay, let's put the straps in first of all. So we put the straps here and here. We could, of course, put the straps on the left and on the right. There's different arrangements which we could do. Another thing we could do is we could rotate this whole arrangement here. So this and this are pretty much the same thing. Simply rotate it through 90 degrees. And then when I add the straps, I've got the straps at the top, and I've got the strap at the bottom, which would effectively be the same as just putting the straps left and right here. So that doesn't look like we've made any significant changes at the moment. And we need to think which one's going to be better in terms of our design rules. And we might think, looking at this, for instance, if you remember that regularity was one of those things we quite liked, if we've got a whole series of different gates, what we'd like to be able to do is to have VSS and VDD as being two parallel lines with the gates in between. So you've got VDD at the top, VSS line here. Sorry, my S is awful. And a whole series of transistors of gates coming in here. And so obviously this arrangement would make that much easier than this arrangement here. The other thing we could try doing is we could move the transistors. So what we've done here is I've taken this transistor and put it underneath this one. Well, actually, this one's gone underneath this one. Or the other way you could think about it is that we've rotated these two transistors here. So the gate, instead of being horizontal in this diagram, is now vertical. And that looks pretty similar to this one. What's the difference here? Well, one of the differences here is if we look at the red poly, that there's more length of poly for our gate here than there is here. And in reality here, what we could do is we could make a via at this point and connect our gate to whatever metal layer it's going to be connected to above at that point there. Whereas here, you need a longer run of the polysilicon. Now, the polysilicon is chosen to be good at being a gate. It's chosen for its work function and so on. It's not really chosen as the material with the greatest conductivity. So here, when you've got a longer length of polysilicon, you've got more resistance. You've got more resistance. You've also got more capacitance because there's always stray capacitance with these lengths of connections. More resistance, more capacitance, more parasitics, slower. So this one looks like the better design. And so by doodling around, we can try different ideas out and say, well, actually, I think this one's probably going to give us the best performance. And then you can start drawing it out carefully in your CAD program. And we can do the same thing with more complex gates. And we can include these merges, which we looked at before, and we can try and choose orientations in keeping with regularity, which is what we looked at again in the previous slide. So you should be quite good at this by now. We've got some Boolean function here. So Z is going to be A or B or C, all ANDed with D. Of course, there's always the invert. So given that, you should be able quickly now to draw the CMOS circuit that corresponds to this. And the A, B, C, and the NMOS side are all going to be in parallel with D in series with it. And of course, that's reversed on the PMOS side. So that should be something you can do fairly quickly at this point. So having drawn that diagram, what we need to do is to think about how to merge the transistors and how to draw the whole layout. So as far as the PMOS is concerned, we can say, well, these are in series. So we've got A, B, C, and we don't need to make separate transistors. They're all in the same region here of active material, and I've made D in a different area of active with its connections here and here. And then we need to do the same for the NMOS. Now, on the NMOS side, we've got A, B, and C. And again, A, B, C for the gates. And remember that in parallel, we needed to have a contact in between, because what we're now going to end up doing is this one here will actually be connected to this, and this will be connected to this. So you can see that here, this is your ground, VSS. These are all connected to each other. So A goes between the ground on this side. I can write G faster than I can write VSS. And this is our Z. And then, of course, B goes between Z and ground. So again, ground is going to be on that side. And then C, again, that's going to be Z. So you can see what happens in parallel is that you are basically just flipping around alternate transistors. We can do a bit more merging, and we can say, well, actually, this is going to be connected to here, so we can merge that in like this. So you can see that for our D transistor connected to ABC, and we can see that likewise on the N side as well, that this point here is common between A, B, C, and D, so you can just join these two together. So if we do all that, what do we end up with? We end up with this. So we've got our gates are just nice straight lines, as short as we can make them. We need to connect up our interconnects. So if we look here, one side of ABC is going to go to VDD, and one side of D goes to VDD. So this will be our VDD connection. ABC then go to a common connection with D, which is our output. And that also, so this is the PMOS side. On the NMOS side, that output is one side of D. The other side of D is this shared connection with ABC, which is joined up in this alternating fashion like this. So this is our VSS, and this is our shared connection here. So that's roughly how the interconnects are going to go. And then what we need to think about is the straps. And of course, we've got everything's lined up quite nicely at the moment because we've got our VDD at the top, our VSS at the bottom. So we can easily put our straps along the top and along the bottom like this. So this will be connecting to the N well. This will be connecting to the P for the NMOS transistors. And then finally, we need to start adding the various implants. So there's the N select. So we need that here for all the N-type transistors. We also need it up here for the PMOS strap, which is connected to its own N well. We then add the P select, which mirrors the N select, so needed for the PMOS transistors, and it's needed for the strap here on the NMOS side. And then we need the N well for the PMOS. So we finally put that around here, and that's everything there, and it needs to be labeled. So yeah, we've got the labeling, that's the NWEL, we've got a VDD, got our output Z, and so on. So we need to label everything, and that is then the complete circuit. One thing we haven't looked at is T-sizing, but we can even put in a bit of T-sizing in our stick diagrams if you wanted to, because we could say, well, here's the circuit, stack depth here is 3, stack depth here is 2. So these need to be width 2, these need to be width 3 times whatever factor we have for P to N, which if we assume is 2, this would be then width 6, and this would be width 2. So that's what's been drawn here, and we've got extra contacts as required. So that's the basics of drawing stick diagrams. Yeah, there's our numbers. Okay, if you go back and think about standard cells for a minute. So if you're doing a full custom CMOS, you're in control. You're drawing everything. You're going to draw your own inverter. You're going to draw every single type of device. But that gives you a huge amount of flexibility at the expense of a lot of extra work. So typically, you're going to be doing this work from a pre-designed standard library of cells, standard cell library, SCL, which typically contains several hundred gates. And that's just about everything you can imagine. So it will have simple things like inverters. It would have more complicated gates for different logic functions. It would have not just CMOS gates, but it would have pre-charged logic. It would have pass logic, and so on. And then, of course, there are latches, multiplexers, adders, multipliers, a whole series of devices. So that takes a long, long time to design. So generally speaking, we're not doing that by hand. It's would be reinventing the wheel all the time and take too long. So, okay, different levels of it. Here's a picture we've seen earlier, which is what happened in the olden days when people carefully drew out every single transistor by hand. Today, it's done by computer. And a lot of these things are just done automatically. But even when it's done automatically, the human brain is very good at optimizing circuits. So although there's a level where we just say, computer, you do it, as long as it works, we're happy. For blocks which are used a lot, it's still worth taking the trouble to look at them carefully and make sure the computer hasn't done something stupid, make sure it's going to work, but also, can we see some optimization which the computer didn't see? So that's the sort of thing where human input is still required. So here we have some sort of layout for a transistor. And if you're optimizing it, you need to know what the parasitics are. So you can then, having got the parasitics, we can then make some sort of model and understand what's going to be the best layout. So we can see the gate length is here. We can see the gate width is the width of the active area here. And these, okay, tell us things like the gain beta, and it tells us things like the capacitance. But we also have parasitics. So these sizes here determine many of these parasitic capacitances. So for instance, if you've got a region here, which is our N-select areas, these are heavily N-doped, it's next to a heavily P-doped area, that's going to give you some capacitance between them. It's a PN junction, and that's going to give you some capacitance. Of course, there's also some capacitance between this N-select area and anything to the outside of it. So you need to work out what the perimeters are, and you can start building up a model of what the circuit looks like. And so you have your ideal circuit, which we've got the gate voltage, got this drain source voltage, you've got some sort of resistor load here. But then you can start putting in parasitics. And there's all sorts of parasitics which you can put in. And you can then model this using something like SPICE. And that's all very well for small circuits, but for real world gates where you have even just a multiplier could have hundreds of gates, the complexity rapidly increases and you need to start making approximations. So you've also got the interconnects to worry about. What's the length and the width of the track? That gives you capacitance, it gives you resistance. Remember that poly interconnects have got high resistance, so we want to use them sparingly, keep them as short as possible. The interconnects can be modeled using a lumped model where you've got a resistance and a capacitance. If you look at a more complicated circuit, you can see here, for instance, there's a load of interconnects. So this is an adder cell. And you can see what they've done here in this particular one is they do use poly for some of the connections, but the poly has been made wider for those connections to reduce the resistance. It also increases the capacitance, but obviously the modeling said this was going to be better. But these all increase calculation complexity. So sometimes we need to look at a cell that's used a lot and try and manually tweak it a little bit. So here, for instance, is the layout for a edge-triggered full latch. So you're going to have a lot of latches in a circuit, so you want this to be as good as it possibly can be. So it's not too big and complicated for somebody to look at that and say, can I make something shorter? Can I merge anything together? Can I improve this in any way? So this is where manual tweaking is still useful. Here we've got an SRAM cell, for instance. Again, a different example. You've got 6 transistors. See them here, count them out. You've got your pass transistors, you've got your bit lines, and so on. So here's the circuit which we saw before. So when we put lots of them together, we have a whole row of SRAMs. But now, if we look at that, we can see, well, maybe we can make some improvements, because these are the power supplies for the different nodes, and they're common. So if you're sharing the power supplies for different nodes, rather than just putting them together like this, you can squeeze everything up. You're not saving a lot of space, but you're saving a little bit of space per bit, and you might have thousands of millions of these SRAM chips, SRAM cells in your final chip. So although you might only be saving, say, 10% of the space per individual cell, multiplied over millions of cells, this becomes a significant saving. So sometimes, yeah, just looking at the circuit, human tweaking can be useful. Okay, so we've looked at how to lay out more complicated devices than simply a transistor. We were looking at inverters and slightly more complicated circuits. We've seen that we need straps which avoid local threshold shifts, and doing this with the VDD and VSS top and bottom gives us regularity, which is good. The stick diagram is an important thing to get to grips with, because they're in a way which we can easily draw gates by hand. But ultimately, we need automated tools to deal with the real world. Okay, that's everything for today. Next week, we'll move on to look at floor planning.